everyone. Let's go ahead and continue working with some application problems. So here we've got a plane leaves a local Air Force base and travels due east. The radar station's 45 miles south of the base, and it's going to track the plane and determine the angle that is formed by the base, the radar station, and the plane is initially changing by 1.6 degrees per minute. So on part A, it says sketch a diagram. So in the worksheets, I'm always trying to say draw a picture, but in the real world, that prompt is not going to be there. So always make sure you draw a picture when working with the trig functions. So we are going to start with this idea that we are looking at a base. And we know that the radar station is 45 miles south of the base. So we know that this distance is 45 miles. And then the radar station is down here. We also know that the plane is leaving the base and traveling east. And I'm going to put an arrow because that plane is going to continue traveling. And we know that the plane is initially changing by 1.6 degrees per minute. So that means that our theta is going to be 1.6 degrees for every minute. So if they've traveled 1 minute, it's 1.6 degrees. If they've traveled 2 minutes, we're going to take that 2, multiply it by 1.6 for 3.2. So that angle is always going to be changing, which is why we have it as an expression of 1.6 times t. Okay, on the visual here, I'm just going to go ahead and draw in some more lines. So if we're 2 minutes in, that means that the plane is going to be here. If we're 3 minutes in, the plane is going to be here. If we're 4 minutes in, that plane is going to be there. So our triangle is technically always going to be changing, but for simplicity, we're just going to leave it looking like this. All right, for part B, we want to define a formula that relates the plane's distance from the radar station. We're going to call this D as a function of elapsed time t since leaving the base. Okay, so we already have our t, we already have our time. And then our d is the distance of the plane. So remember the plane is here. And so remember that this plane is always moving. It's always going to the right. Okay, so when we look at this right here, our angle is this angle right here. Okay, so when we're creating our formula, we're going to be looking at using this distance because that's what we're trying to find. And then notice that we also have our 45 miles. So if we look at our triangle, this right here is our right angle. That means that the D is going to be the hypotenuse. And then the one side that we know is going to be the 45 miles. That is next to our angle. So that means that this is going to be our adjacent side. So when we think about our functions, we have our sine, which is opposite over hypotenuse. Our cosine is adjacent over the hypotenuse. And then our tangent of theta is opposite over the adjacent. So when we look at those three functions, we want to determine which one to use based on the information that we have. So since we, in our triangle, are looking for the d value, which is the hypotenuse, and we are given the adjacent side, we want to use the function that has the hypotenuse and the adjacent. Okay, so if we come over here, you can see that the cosine is the trig function that has the hypotenuse and the adjacent. So that means we're going to use the cosine for our relationship. Okay, so coming down here, I'm going to write it as cosine theta is equal to the adjacent over the hypotenuse, which means that we've got cosine. Our theta we know is 1.6t equal to the adjacent, which is 45, over the hypotenuse, which is d. Okay, and this right here gives us our relationship. And it does say in the question, define a formula where we want the plane's distance as a function of time. So what that means is we want distance equal to some expression where there's a t within that expression, right? So we want to isolate our distance, or we want to isolate our d value. So when we look at this expression, we want to isolate this d. To do that, what we're going to do is multiply both sides by d so that the d's can go ahead and cancel. Then we are left with d cosine of 1.6t is equal to 45. And then to get d by itself, we divide by cosine 1.6t from both sides. So now we have a formula where we have distance is equal to some expression with t as the input variable. And this right here becomes our solution. So this formula will tell us whatever distance the plane is at any given time. Okay, on part C, we are again going to be creating a formula, but this time we want to relate the plane's distance from the Air Force Base, we're going to call that C, as a function of time elapsed. Okay, so if we go back up to our picture, let's go ahead and label the plane's distance from the base. We're going to call that C. And so we're still using that same angle of the 1.6t, which means that C is going to be the opposite side of that angle. Okay, so since we are looking for the opposite side, and this adjacent side was given to us, we're going to look for an equation that allows us to use the opposite and the adjacent in our formula. Okay, so coming over here and looking at the sine, cosine, and tangent, we want to use the one that uses both opposite and adjacent. And this time you can see that the tangent function is going to be our best option because it has the opposite and adjacent. Okay, so our tangent of theta is equal to opposite over adjacent. Okay, so we're going to go ahead and plug in our variables. So we get tangent, our theta is going to be 1.6t equal to the opposite, which we are calling C, and the adjacent is going to be the 45 miles. Okay, and so in the definition here it says define a formula that relates the plane's distance from the Air Force Base as a function of time. So again, we want distance, in this case our C, to be equal to some expression with t as the variable. So basically that means we want to isolate our C value. Okay, so we are going to isolate that C, so which means we're going to multiply both sides by 45. So the 45's cancel. And notice on this particular problem, we don't have to do any further work because we have now isolated our C value. And this right here is our solution. So the plane's distance from the Air Force Base is going to be equal to 45 times tangent of 1.6t. On part D, we want to use our formula from part C. So that means we're going to be using that 45 tangent 1.6t. And we're going to complete the following table, and I want you to round to 4 decimal places. Okay, so I'll go ahead and show the work for the first 2 parts, and then I'll let you fill in the rest of the table. So I'm just going to go ahead and do the work right here. So when we have an input of 0, we get 45 times tangent of 1.6 times 0, right? So we're plugging in 0 for t. When you plug that into your calculators, you're going to get a solution of 0. Next, we're going to do 45 times tangent of 1.6 multiplied by 0.5. Okay, so in your calculators, it should be able to handle that. If you have one that doesn't, make sure you take 1.6, multiply it by 0.5 first, and then do 45 tangent of that value. And we're going to get a value of 0.6284. Okay, so go ahead and pause the video and fill in that same column for the minutes 1, 1.5, and 2.0. Okay, go ahead and check your solutions. And then now what we want to do is find the change in C over the change in T. So this right here is really just your slope. It's also known as the average rate of change. Right, so that idea is that it's really just the change in y over the change in x. So you might be familiar with it as y2 minus y1 over x2 minus x1. So in this problem, for that first one, we're going to do 0.6284 minus 0 divided by 0.5 minus 0. So just the change in the y's divided by the change in the x's, or the inputs. When we do that, we get 1.2568. Go ahead and repeat that for the other values. So go ahead and find the slopes. Okay, these right here are the values for the slopes, and you can see initially when the plane is just taking off, that slope is very similar to each other, which is why I wanted you to round it to the 4 decimal places, so that way you can see that there is a slight change in the plane's distance. Okay, and then for this question it says, describe how the plane's distance from the Air Force Base, measured in miles, changes as a function of time elapsed during the first 2 minutes. Okay, so if we look at our table of values, here we can see that the input is telling us that this is the 2 minutes, right, which means that time is increasing. And then the next column, we have the plane's distance, and you can see that this distance is increasing. And then when we look at the slope, these slopes are getting larger. Very small, but they are increasing. Okay, so we could say that as the time is elapsing, or time is increasing, the distance from the base increases, and the change in the distance increases. All right, we're going to continue working with that same formula. So for part E, we're going to do the same thing, but now notice that the t values are larger. So we have 42 minutes, 45.5 minutes, and so go ahead and fill in the table just like you did before. So go ahead and pause the video while you do that. All right, so these right here should be the solutions. Okay, so again, just like we did before, you're plugging in t into the function to get the plane's distance, and then you are finding the slope for that third column. Okay, part F says, describe how the plane's distance from the Air Force Base C changes as a function of time elapsed between 42 and 56 minutes, right? So that is our table here. So just like before, we're going to look at each column separately. So our time is increasing. If we look at the plane's distance, the distance is increasing. And then when we look at our rate of change, it goes from 10 to 21 to 59 to 1,719. So that means that the rate of change is increasing. Okay, and then putting that all together, we could say as time elapses, the distance from the base increases, and the change in the distance is also increasing. Okay, there is a second part to question F. It says, are these values realistic? Why or why not? And so the solution there is that at some point the plane would stop speeding up and travel at a constant speed. So these values are not realistic. So at some point the plane will have a steady speed. or a constant speed. Okay, so in part G, you will see that there is a graph there. I want you to go ahead and plot the inputs and the outputs. And for time reasons, it works really well if you have the time be a change of 4 for your increments. So the x-axis will be 4, 8, 12, 16, etc. And then the y value, or the distance, if you do increments of 30, so you'll have 30, 60, 90 on the y-axis. That works really well to plot all the things that you need to plot. Anything beyond that on the graph does not need to be plotted. So go ahead and pause the video and graph those points. All right, so this right here is what your graph should look like. Make sure you have labeled your input and output. So your input is time, since leaving the base in minutes, and then the output is going to be the distance in miles from the base. Also, I want to point out the shape of this graph. When we were looking at the table of values, we said the distance increases, and we also said the rate of change increases. And you can see that visually on our graph. So as we read it left to right, it is going in an upward direction. So that is the indication that the distance is increasing. And then the rate of change is determined or shown by concavity. So since the rate of change is increasing, that means the concavity is going to be up. And you can see that visually, that we have the concave up shape. All right, and then let's go ahead and take a second and talk about the realisticness of this graph. So realistically, the plane will not continue to speed up and will at some point reach a cruising speed or a constant speed. And so at some point, this graph is going to become linear. I don't know exactly where it's going to happen. I'm just going to randomly choose a point, and then we will have a constant speed from there. All right, that is the end of this worksheet. We'll see you in the next video.